Welcome again. We're back to basic sciences for the RT, and moving along, we're going to be talking about some changes of state. Alright, getting right into it, liquid solid phase changes. These are melting and freezing. So all matter can move from one state to another. Some of it happens easily. Some of it's going to require some extremes in temperature or heat to make it happen. So if you have an ice cube, you can melt that down to water pretty easily just by leaving it out on the counter a little bit too long. But if you have some steel bar and you want to change it to a different change of state, maybe a square, you need to pound it out to a plate, you're going to require a lot of heat to get that thing to melt. So phase change is what happens when you reach the special points called the freezing point or the melting point. And these are the points on the temperature scale where your phase changes from a liquid to a solid or the solid to a liquid. There's some physical things you can do to an object that's going to change its melting and freezing points. Pressure is one of those things you can change. So when pressure surrounding a substance increases, the freezing point also goes up. And it's also easier to keep things solid when they undergo great pressure. Generally, solids are less dense than liquids because their molecules are close together, and the freezing point compresses the molecules into smaller. Alright, so the properties of liquid. So we know that liquid will flow. We also know that liquids are going to assume the shape of whatever container they're in. We also know that liquids are going to exert a pressure. So, if you ever jump into your pool, or if you're not lucky enough to have a pool like me, you go to the other pool, and you dive down, and once you get to about 10 feet, you can start feeling the pressure in your ears a little bit. So we know there's some pressure that comes from being in the liquid. And this also causes some unique things like surface tension and some other forces that we're going to talk about in the next couple of slides. So the pressures in the liquid. First, we're going to be talking about this handsome gentleman up in the top corner, which is Blaise Pascal. He was a French scientist who developed his own principle or law because he couldn't figure out how to lift up his SUV when he needed to get under it. Well, that's not exactly how it happened, but it's fun to think about it. So, Pascal's law is a fluid at rest in a closed container. A pressure change in one part is transmitted without loss to every portion of fluid and to the walls of the container. So here on the left, you'll see when you condense the liquid on the left side, you're actually going to be able to lift that object on the right side very easily. This is because the pressure is equal to the force divided by the area in which it acts. So what we were able to transition this in the real world is how hydraulic systems work. And this is how we're able to lift things that are 10 times heavier than the force you need to push down. Pascal also discovered that the pressure at a point in a fluid at rest is going to be the same in all directions. The pressure would be the same in all planes passing through a specific point. Again, this is Pascal's law. Alright, next up is buoyancy, is Archimedes' principle. Yeah, there's a double S there. So, this is the physical law that revolves around buoyancy. This was by the Greek mathematician and inventor Archimedes, who after he had a hard day out inventing things, and he filled up his bathtub, and he was looking forward to this nice warm bath all day. So he fills it up right to the rim, and he gets in, and all of a sudden all this water flows out over the sides, and he's all mad because now he has to clean up all this water. And then he's like, no wait, I just discovered a law of fluid dynamics, and he jumped up and it went, Eureka, I know how to make boats float and stuff like that. But not exactly how it went. But so the buoyancy is that a body completely or partially submerged in a fluid, liquid, or gas at rest is acted upon by an upward or buoyant force, the magnitude of which is equal to the weight of the fluid displaced by the body. And we need to remember that the volume displaced is going to be equal to the volume of the object completely or fully immersed in that fluid, or to a fraction of the volume below the surface area that is partially submerged. So, if you take a volume of 3 and a square and you put it into the bathtub, it's going to block out, or it's going to overflow with an equal volume of 3. Or say when this dude Archimedes jumped in the tub, he was only half submerged. So whatever the volume, if you could calculate his surface area or BMI or whatever from the waist down or however deep that, maybe it was neck deep. We don't know. But whatever was submerged under the water was going to be an equal amount displaced. And it's also important that the weight of the displaced portion of the fluid is equivalent to the magnitude of the buoyant force. So the buoyant force of a body floating on the liquid and a gas is equivalent to the magnitude in which the floating object in opposite directions. So the object neither rises nor sinks, it's going to float. So when a ship that is launched into the ocean until the weight of the water displaces is equal to its own weight. So if it's a 3,000 pound ship, it's going to pop down until 3,000 pounds of water are displaced. And then once it reaches that point, you're going to have full buoyancy, and that's why your boats float and we're not sinking anything. All right, next up is viscosity. Viscosity is the quantity that describes a fluid's resistance to flow. So imagine having you have your cutting board or something, and you want to elevate it up or set it straight up in your kitchen. Imagine you take a couple liquids. So we're going to say first, if you take a drop of water and you put it on the top of your cutting board, it's going to flow right down it. Now imagine if you switch over and do a drop of honey. Now you're going to put it there. It's going to take a little bit of time, but eventually it's going to get to the bottom. Imagine you take another liquid that's not very viscous, say ketchup or barbecue sauce, and you put it on the top. It's not moving very fast, but eventually, when you come back, it's probably going to be either dried up and stuck where it is, or maybe somebody came and decided it looked good and licked it up, or the cat ate it. But if it didn't dry out, it would eventually, slowly get down to the bottom of that cutting board. So that we say that the thicker the liquid is, it's not actually thickness, but it's more viscous. And with viscosity, we have this concept of laminar flow. So this is with a type of fluid flow in which the fluid travels is smoothly or in irregular patterns, in contrast to turbulent flow. So turbulent flow is when it kind of goes in all different directions, but that's a different lecture. We're not going to talk about that. So laminar flow. This is also called streamline flow. Velocity, pressure, and other flow properties at each point in this fluid remain constant. An important thing that we're getting into with laminar flow, so if you have a fluid going through a straight pipe, it's considered the relative motion will develop these kind of rings around it. So what's called as the outside of a fixed pipe will be moving at increasing speeds as the center of the pipe is approached. So when we have a fluid going through a container, you see here, you're going to have the center, the very center is going to have the fluid is going to be out a little bit further. We move back a little bit, there's another streamline here, we keep going back, and then the ones that's in contact with the sides of the container are actually going to be moving the slowest, but it kind of forms this meniscus out here where it kind of peaks out, and the center is going to be moving the furthest out. And this is what happens if you're pumping oil through a tube, or this also happens in your blood vessels, but there's not going to be like that empty space there. And there's also some other properties of elements in your blood, like your platelets, your cells, other things like that, that are going to cause some changes in the viscosity. Next up, cohesion and adhesion. So cohesion is the attractive forces between like molecules, and adhesion is the attractive forces between unlike molecules. So we have here is, on the left you can see our water molecules. Cohesion are them holding hands, and adhesion would be them holding on to a rope, trying to get away from each other. I guess they're alike, but they don't really like each other. So another thing is this can cause some differences in your meniscus. Menisci. So this depends. The meniscus depends on the strength of cohesion and adhesion. So with water, you have adhesion is stronger than cohesion, so you're going to form a concave meniscus. So it's going to be, sticking to itself stronger than it is to the sides of the wall. It's not exactly sticking, but it's a way to think of it. Then when you have another element like mercury, cohesion's stronger. So it's kind of hard to see here. It's gray on white, but on the right you can see it kind of bows upwards, whereas the water, the meniscus bows downwards. So the water is concave, and the other one, the mercury, is convex because it has stronger cohesive forces. That brings us to another interesting topic, which is surface tension. So the cohesive forces between the liquid molecules are responsible for this phenomenon. The molecules at the surface do not have other like molecules on the side. So we have, they're holding hands outward with each other, but upward is air, so they're not able to hold on to that because that's an adhesive. So it ends up forming something that's similar to a film. And when an object moves through the surface, and it can cross that surface tension and be completely submerged. So we have a couple examples of surface tension here. On the right, you see a swimmer. He or she, I'm not exactly sure this was from the Olympics, but he was about to break the water surface there. So you can see that the molecules of water are still holding themselves together. So he's about to break the surface tension there. And on the left there, you see this is an astronaut. He's on the space station. So this is a little differently. This is a zero gravity experiment that they did. And you can see here that they put the droplet of water, and because its cohesive forces are so strong, it forms itself into a perfect sphere. This is different than, say, if you took a water droplet on Earth. Because of gravity, it would form itself into a droplet, not a sphere. But up in space without any gravity, it's going to form itself into a sphere. And since its cohesive forces are so strong with itself, it actually will be bouncing back and forth like he's going between those what are they, paddles. Another one to talk about is Laplace's law. Now, I wasn't able to find a picture of that fella, but this is another law that states that pressure varies directly with the surface tension of the liquid and inversely with its radius. So surface tension increases the pressure inside of a liquid or drop or bubble when there's outside pressure performed on it. Another interesting thing is, so paratroopers, if they ever are jumping out of a plane and they have to make a water landing where they're going into the water at a pretty high force of speed, they're going to need to break the surface tension of water, or it's going to be like hitting they're smacking on concrete or something. Another thing that they'll teach you, and if you ever go to jump school for whatever reason, is when you're about to go into the water at that high rate of speed, is you got to clench your butt, or else you're going to get yourself a water enema. All right, and capillary action. This is another property that we're going to talk about. So this is when a liquid will travel against gravity, and this is because of cohesion due to adhesive forces and surface tension. So we have this picture here. So they took some type of a cloth, and we're going to say that's grape juice, wine, pick your poison. So when you put it in those two containers, the capillary action is actually going to bring the water from the one container to the other one against gravity. This is some other interesting things. Like, this is what happens when when you have a tree outside where it's pulling water up from the ground. How do the rest of the tree get water? Well, capillary action. The water is so strongly cohesive that it goes up, through the roots all the way against gravity to the top of the tree, so the whole tree can get its liquid and remain healthy.